Hello and welcome. This is a video for my collaborator Emily J. Allen from the Department of Psychology, Auditory Perception and Cognition Laboratory Group at University of Minnesota. And in this video, I'm going to show her how I would segment the Heschl's gyrus, only Heschl's gyrus, based on very high resolution 0.35mm GRE data. Okay, so let's have a look at the data first. In ITK Snap, I'm going to introduce the images that we have. So here I have a T2 star weighted image that is recorded at 0.35mm isotropic resolution at 7 Tesla of a living human brain. And this is already pre-processed by Emily. So we have a nice pre-processed data. And this is the average of all the echoes. We had 6 echoes that was averaged to this image. And nicely, just as a quick quality control, you can see that you can even see the cortical layers directly with your eyes in this data. As you see here. If you are interested about more details about this data before we write a paper with Emily about this, you can refer to my 2022 paper and see how we get GRE acquisition 0.35mm images at 70. But this is not so important for today. So today I am going to show how to segment the Heschl's gyrus region and only Heschl's gyrus region based on this partial brain coverage data and only relying on this echo average pre-processed T2 star weighted image that we acquired after processing 0.35mm data. A few details here, you can see that actually this image is at roughly 0.175mm isotropic resolution because during the pre-processing we upsample the data, motion correct, and average everything together. This gives a bit of an advantage. But okay, like now I'm going to just focus how I would do segmentation on this data. Only in one region, Heschl's gyrus. And not really focusing on the rest of the brain or not using any T1 weighted image and anything like that. Okay, so first I would like to introduce 3 types of images that I'm going to use to segment this dataset. First one is the pre-processed T2 star weighted image, as I have shown you. The second one is a filtered version of this image that I use as a supporting image when I'm struggling to decide about the cortical boundaries or white matter gray matter boundary. And here, if I set to the same contrast, you will see how similar they are. 260, 640. Okay, now we are at the same contrast. And here is the difference between these two images. So you can see that this filter that I have used, which is talked about in this page, in the segmentator software package, there's an implementation of it, and you can read more details here, but I will not talk more in detail. So I have used this filter to smooth this data a bit. And later I have computed the gradient magnitude derivative of this data as an additional image that helps me to decide on the white matter gray matter boundaries. And here is the gradient magnitude image. If we optimize the contrast a bit, you will see that this image basically shows in a better way, in a bit more quantitative way, the areal boundaries. You can see that between this image and that image, in some areas we have a clearer boundary, white matter gray matter boundary, which is an issue when you are segmenting the Heschl's gyrus, because the boundary between the gray matter and the white matter at certain places in Heschl's gyrus is very gradual. So we try to kind of enhance that as much as possible. Okay, so I loaded these images. I am going to focus on the, let's say, the right hemisphere Heschl's gyrus for this video. And now I'm going to show this a bit of a brute force method. Okay. So first thing I do is to go to this snake tool go to segment 3D, and change the threshold to a one-sided threshold. That is very sharp. This is a bit of a like using this tool in an unintended way to create a scoop, I call, or scoop of interest or bubble of interest. So I set it like so, lower threshold to the minimum, smoothness to the maximum, lower only, close. I click on next. And here you can see that there's a button called add bubble at cursor. So this basically adds a bubble at the cursor that we can determine its radius. So I am doing it because I would like to only focus on a bubble or a scoop, I call it, around Heschl's gyrus, so that I am not going to see the rest of the image once I create this mask. So here I'm going a bit back and forth and making sure that Heschl's gyrus is nicely included. Mostly on the medial part, this is an important region to check. So I think my bubble includes Heschl's gyrus pretty nicely, at least to start segmenting. And once it is determined, I can also make it, for instance, 20, I believe, millimeter in radius. I can click on next. So this step basically puts a spherical segmentation bubble around that region. And there's another usage of this tool, but now I just want this bubble and nothing else. Therefore, I'm not going to iterate or not touch on any other parameters, but just say finish. And at the end of these steps, I have a nice little bubble around Heschl's gyrus. Then I'm going to save this. Let's call it right hemisphere scoop of interest. Okay. Once I have that scoop of interest, I'm going to take my images and I'm going to mask them with this binary file. For that, I'm going to use NeMath. It's installed in my computer, but you can use FSL Maths or some other AFNI program or whatever you have. It's just a simple binary mask. So I'm going to take my initial image and I'm going to mask it using mask function. Give my scoop of interest. And then here, I'm going to give an output name called scoop of interest right hemisphere. Let's save it like this. So I'm going to repeat it for all the other images. Okay. And for the Gromag, gradient magnitude. Oh, I forgot to tell where this is coming from. I will circle back to that. So this Gromag derivative is coming from, as I computed for this specific video, from Laney. There's a new or new-ish, I implemented, I think last year, program called LN2 Gromag. You can see here the source code. But basically, if you run this on your input data, it will give you that gradient magnitude image that basically highlights the edges in the image. Okay, let's go back to ITK Snap and let's load our masked data. Okay, now you can see that we only have the scoop of interest isolated from all the other tissues around it. This is good to just keep our focus in here at the initial stage of the segmentation. Okay, so once I loaded these three masked maps, and here I'm really going to show you the maybe the most brute force method of doing it. I take my tablet, drawing tablet, and I start just segmenting manually. This is a small region of interest, so I think it's like let's start like this and see how things go. So I start from the most medial part, or as most medial as possible, and follow roughly the boundary of the Heschl's gyrus that starts there, I can see, and follow from medial to the lateral side. So basically in this direction, let me show like this. So start from here and whoop, I'm going to sweep through here within the scoop. Okay. But instead of going through every slice, I am going to go every, let's say, maybe fifth or the seventh slice, and I will come back to how we like work with that later. Just trust me on it for now. Actually, let's do a little calculation. So let's say the medial most slice is, let's say, around here, which is 222, slice 222 on X. And probably we will sweep up until around here, which is like 100. So we have 120 slices in total to segment at the beginning, at least. So 122, let's say. If we segment every fifth slice, we are going to go through only 24 slices. If we segment every seventh slice, I go with the odd numbers for a reason, like either 3, 5, or 7, because of this next step that I'm planning to follow up on this one. So 122 divided by 7 is 17 slices, like 18, which is pretty manageable. So which means that you need to do this drawing work for 18 times. For 18 slices. Okay, now this is what I mean. So let's start from here. Now let's go from medial to lateral. Whoops, this other way. 1, 2, 3, 4, 5, 6, 7. And here I draw again this boundary. So hopefully you see where I am drawing it. All this dark stuff are pile veins or pile vessels actually, because some of them can be arteries. And I know that the white matter gray matter boundary is here and gray matter CSF boundary is over there. So I am now basically roughly drawing that outer gray matter boundary. And I'm not drawing white matter gray matter boundary to begin with. It's like white matter plus gray matter included up until the CSF boundary of Heschl's gyrus. Okay, now let's go. 1, 2, 3, 4, 5, 6, 7. It is a little bit like sculpting, doing this work. And you will see that this rough outline will become more and more polished in the future. 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. So you see that I am stopping basically when I hit these dark dots, because they are a good indicator of the outer gray matter boundary. And I use a very large brush because I don't care about minuscule details for now. They will be polished out later. 5, 6, 7. 2, 3, 4, 6, 7. 3, 4, 6. So if the brush is too large, we can decrease the size of it a bit, like to get these gyri nicely. 7. We only care about segmenting the superior portion of the temporal lobe where Heschl's gyrus is. Therefore, I don't care about this more inferior part. Like we are not going to analyze that part. So okay, 1, 2, 3, 4, 5, 6, 7. 6, 7. Okay, 1, 2, 3, 4, 6, 7. 6. Okay. I think we have more or less arrived to the more lateral side. I can notice that by the shrinking of the scoop as I'm moving from medial to lateral direction. Okay. Okay. And the other nice thing is that once you have a couple of slices and you update, you will actually start seeing the geometry of what we are doing. And in time, this will make more sense. I mean, you can already, or people who spend time on Heschl's gyrus can notice that this is the medial part, this is the lateral part. You can see that it's splitting a bit. And we are filling in roughly these areas. Okay, well, let's do one more time. Okay, one more. Okay, I'm happy with that. So now I'm going to save this segmentation as segmentation Heschl's gyrus version 01. Okay, so now this segmentation is saved. Now I kind of forgot, but I have several scripts that I'm using quite a lot to do what I'm going to do now. I'm just thinking which one I should use. Okay, there's like one Python script that I use most of the time, and this is like something I should implement in Laney actually. Just make a simple tool out of it. I can send you this script. Morphology. This is like a handy script that I wrote back in the days, and I keep forgetting to put this in Laney actually. But together with this, I should do it. But anyway, like here, basically, you would give a nifty file, and we are going to do some morphology operations on this to fill in these gaps that we skipped over. We are going to do a closing operation, which is basically dilating and then eroding stuff. And I'm going to have 3 steps of dilations. So if we skip like every second slice, so each slice grows to the sides. Like when you put one iteration here, dilation, it grows to the like one to the right, one to the left, also up, down, everywhere. But in 3D, it grows one by one, let's say in the medial lateral direction. So that if I had segmented, for instance, every third slice, it means that if I put iteration 1 here, like this slice will grow here and this slice will grow here and they will meet. So they will fill in the gap. I put, instead of 3, every 3 slices skipping, not 5, but 7, which means that here I need to put 3 iterations because they will grow 3 steps here, 3 steps there, and this 6 slice gap in the middle will be filled by this dilation operation. Then I'm going to do 3 steps of erosion, like this equal amount of step of dilation and erosion called closing operation. This is a morphological operation. And it's just handy to fill in stuff that you know more or less the shape should match. Okay. Yeah, I'm just going to copy it in a folder that I will send to you, share with you, so that you have direct access to it. Okay, Python scripts, morphological dilate erode, and I'm going to put this into Emily segmentation. So now I can go to there and just run that script. So let's keep this here for future. Remove my main sublime. Okay, now once it is done, it will save it with this underscore close suffix. Now let's load it and let's see what happened. So you can see that in between parts are now filled in, and we can update and see that stuff is basically filled in, right? So this is a way to basically speed up these early stages of this sculpting that we are doing. Okay, now once I have this filled in, now the second stage of my segmentation, I'm going to save it as, let's say, version 2 already. Now I can switch to another view and fill in the pieces a bit there. So just to smooth out the edges. For instance, let's have a look at here. My computer is slightly slower because I'm recording at the same time. Okay, let's adjust the contrast. Sometimes it's handy to see the edges here as well. They can guide you. Okay. Now, that's, as I said, it's similar to sculpting. So every time we do this filling in and polishing a bit, we can go a bit smaller. Okay, I see, for instance, that part can be taken. So now I can do every fifth. Still filling in stuff, polishing it a bit. And now you notice that I am only filling in, which means that I'm not reducing stuff, because the way you like add material or subtract voxels, it interacts with how you plan to do closing or opening operations, the one I showed. So closing works when you fill in stuff, and it fills the in-between stuff that you already filled in by skipping. Anyway, like hopefully you will see how I am doing it by watching me do it. Okay. Going 5 by 5. Here. I mean, probably you might be a bit slower doing it at the beginning because this is my, I don't know, 20th, 30th subject that I segment their Heschl gyrus using this method. I am noticing like pretty straightforwardly the geometry of the Heschl gyrus there. But you will speed up very soon, actually, very fast. Okay, now let me see how is the geometry here. Okay. Okay. The best view is this medial lateral direction to notice where the Heschl gyrus and so forth is. Okay, now I filled in a bit more. I'm going to save it and I'm going to use the same trick. Let's put version 2 here. And now we can do just 2 iterations. Okay, the same idea. Let's load. Things are filling up a bit more. You can press on this button, 3D crosshair mode, and this allows you to jump on the geometry in 3D. This is also pretty handy. Okay. Now let's do a bit of more finer work. Let's say here. Now I'm going to do every 3. You can also see the edge from this mushroom from here. There are some parts that are easy, like that are hard to decide, and that's just the nature of the data. So there will definitely parts of Heschl's gyrus where we will be less sure than the others, but once we do, for instance, back and forth with you, with me, a couple of times, we will get into a good consensus. And I think it will be fine. Like, basically what I'm trying to say is that if you cannot, like, very clearly decide on whether there's a border or not, don't stress over it too much. Like, we will figure it out. From the gross anatomy, macroscopic geometry, we can figure out, like, how the border should go. It's all about iteration, this thing. And since luckily we have a small region of interest, we can just do this maybe a bit more manually and without worrying about making it fully automatic and so forth. But we will at least know that it fits to our data exactly, this main data, right? At 0.175 millimeter nominal resolution. And once we later compute layers and other stuff, we will know exactly, like, because we did the full quality control, full segmentation, and we will know the geometry very well in our subjects. And at the end of the day, like, you spend a day for one subject, I spend a day for another subject, and we have, like, however, like 10 subjects in total. In a couple of months we are done. Like, not even doing it every day, I mean. And we know that everything is very well quality controlled and there are no sort of automatic segmentation related weird biases. Also, like, note that this data set is, no one is using this data, so there is nothing that works on it so nicely. And I don't want to turn this project into a segmentation methods development project. This just works, and let's roll with it. Okay, we filled in a bit more there. Let's check the medial side a bit more. Okay. Yes, I'm also trying to not over focus on the minor details, as this is the from rough to fine process. Let's save it as version 3. And you see that I keep track of my segmentation through these versions. It's not like each version has to mean something, it just means that I am iterating over. Okay, let's run the closing operation. Yep. Okay, now let's smooth out these filling in artifacts. There's an easy way to do it, and that is using a bit of Gaussian smoothing and then re-binarizing the data. Again, like, I will show you how I use it with the NeMat or FSL Mats program. Probably you can do it with AFNI. Okay, NeMat. Put the data. Then I will activate the Gaussian smoothing operation. It takes full width half maximum as the second parameter, and our voxel resolution is at 0.175. It doesn't matter so much, but roughly your minimum full width half max should be your voxel resolution. Since we are doing fine work, I'm going to just put it 0.5 millimeter resolution, so it will smooth the data. And once it is smoothed, every value will become a value between 0 and 1, because we had a binary image at zeros and ones. Now we smoothed them. So now new voxels that are after smoothing might have a value between 0 and 1, meaning that it can be 0.6, for instance. Anyway, and since that's the case and we want to rebinarize it, I put threshold here, 0.5, so that everything below 0.5 will be 0 and everything above will stay. But I want to put it to actually 1. This is what I call rebinarizing, and that you can do with a bin label or parameter there. And let's save it as version 4. So this will run a little while, but it should be not so slow. Okay, done. Version 4 is here. Let's load it and see the difference. Whoop. See? It's already way better. Way better. See? Okay. So you can easily notice the features of the Heschl Gyrus. Medial, lateral. You can click on it to understand which direction it runs. And basically we are going to analyze like a disk that is sitting here. Okay, now let's continue to polish. Okay, let me try to optimize the contrast a bit better. Okay. So as you see now, I'm going through a bit more in detail. You can also, by the way, make it continuous update so that you see where you are editing, polishing. Here, maybe I have it better in a different view, this region. So I'm going back and forth, and in the same time I am pressing page up, page down, or the buttons that I have assigned to be page up, page down on my tablet, so that I can focus on one region and continuously keep filling in. So after the initial stages, which is going slice by slice, I switch to this strategy of painting because I find it more useful, more efficient. My eyes are always focusing on the same region. I have a continuous understanding of the geometry there. I'm thinking about that geometry and filling in the border. And always, whenever you see this big tubular structure that are kind of sandwiched like this in between two gray matter, that's the outer gray matter boundary. They are the pile vessels. So stop there before going into them. It is not as you see it in the T1 weighted images. So definitely, if you are tuned to seeing the outer gray matter border in T1 weighted images, this will feel strange. But eventually you'll get there. And the registration between T1 weighted lower resolution images and this one that is way higher resolution, it is like never as good as you want. So there are all these ways of going through segmenting T1, registering it, blah blah, but for the precision that we are aiming at, to analyze this really in high detail in laminar resolution and studying the laminar patterns in the Heschl's gyrus, hopefully, like we need this type of precision, and like going through all these hoops to segment T1 weighted images, register it on these, which is between 0.7 to 0.35, and they just don't work as good as it. Like, I mean, you end up doing this work anyway. So my point is that why not just segment our region of interest directly and be done with it? That's my mindset. Many people don't understand it, but also, yeah, many people don't do this type of high precision work in one region of interest, as I've been doing for my whole career, basically. So what do they know? For like whole brain stuff, of course, like we cannot do it for whole brain. That's clear. If you want to do fancy whole brain laminar analysis, you cannot do this. It will just take too much time. There are other methods that I use for that to polish more fastly whole brain, but this is now good enough for what we want to do. Did you? This might be wrong. Okay. It's a bit too bright. So I see that there's a little sulcus there that we need to open it up now. Okay, now let's switch to this opening up mindset. Let's save this. For opening things up, I use brush size 2, not 1. It's better to just be a bit rough at the beginning, and I select clear label. Okay, now I see that this is a sulcus here, because this is a pile vessel. And you see I'm kind of following that darkness because it indicates the bottom of the sulcus. They sit there most of the time, these pile veins. So they are a good indicator of where your sulcus is. Okay. See, I'm just opening it up based on that dark thing. That guides my outer gray matter boundary. Hopefully it's visible like nicely here. Maybe I set this up for you like this. Okay. Okay. What went wrong? Okay. Let's fill this up a bit. Okay. Now let's save this. So now I'm going to do a combined polishing step. So I go to new math, put the thing. This also has dilation and erosion operations in it, but it's a bit slower than the Python script, so that's why I didn't use that one. So let's say arrow. This for eroding. So it erodes the binary map. I'm going to smooth it a bit, this time a bit smaller kernel, 0.35. And the same threshold, 0.5, binarize. And now because I eroded it, I'm going to dilate it back. Deal F, it's called. Call it 5. Okay, let's see the result of this. And the operation is done. Let's load that. Okay, see, it's getting better. Okay, now I'm going to switch to labeling white matter. Okay, for that I'm going to change my active label to label 2 and paint over, this is important, to label 1. So it only paints over the reds basically. Okay, let's save it and let's start working on the white matter. So again, you can have the same idea in a way of going through skipping slices, but then it becomes a bit complicated, let's say. Or how should we do it? Yeah, let's stop that skipping for now. Let's go now slice by slice. Oops. And now see that I am only caring about really just the superior boundary. Okay, one by one, let's draw. Doesn't need to be so precise. It's just good enough. Okay. Hopefully you can see that I am following that contour. Not exactly, but as precise as I can be. Being exactly precise is not needed at this stage. Because when you are in a bit and off a bit in some slices and you are doing it for every slice like this, the next step that I'm going to show you that's going to use another tool implemented in Laney actually that I did. It will take care of those, like one slice being a bit too in, one slice being a bit too out type of things. So now this is, for instance, what I'm talking about. Like there are some places in Heschl's Gyrus, it's like really hard to decide where is the white matter, gray matter boundary. And those places I try to basically found where I see the boundary. Like here, I really see it. Like see there. And here, I really see it. Like it's there, the boundary. And in between, I try to get like a more informed opinion by going through other images like this one. It's really not visible. This one is also really hard. I look at the gradient magnitude. I see that there is a little bit more, like maybe like this. It's a bit tricky, but in those cases, just try to follow the same thickness as you had in the rest of the parts that you can see. And actually, this goes back to our eventual paper, because I think that effect that we are seeing here, the really like the gradual, very gradual change between the white matter T2 star weighted signal and the gray matter T2 star weighted signal being almost the same, I think this only happens in A1. And we will just, I think, at the end, pick up this in our analysis. Because here you see like the gray matter really looks different, and there it really looks different. But there in the Heschl's gyrus, more on the anterior part of it, as it should be, it's really hard to detect a boundary. Sometimes it helps to zoom out for you to see. Sometimes it helps to just look at the gradient magnitude image. But yeah, we just have to roll with it like this for now. Okay. I'm basically manually interpolating in between in another ways. I see this part, I see that part, and I see like a hint of boundary there, and I fill in. Yeah, this is like really hard, for instance, here, but like only that part you see. And I think that's actually where the A1 is. It follows with the other literature. I'm not making it up based on this data. We have other types of histology images as well to support this judgment. So this is not at all like just looking at the data and making up something that fits what I'm seeing in the data. No. We will support this claim based on other publicly available histology datasets. Like Big Brain, we can have a look at the AHEAD dataset that I have experience with. Multiple different contrasts, so that will come later as almost a control analysis that we can establish based on the in vivo data details that we pick up here. This one is really hard. I have to say that my images that I did get here in Maastricht and the more recent ones with 3D EPI instead of just GRE, I have to say that they look a bit more higher SNR than these. I could see the boundary more clearly there. So there is definitely a bit of a noise issue that we are struggling with here. Like it's a bit too low SNR. Not to the level that it's unworkable. Like as I mentioned, like we can make these heuristic based judgments on where to put the Heschl's gyrus boundary for white matter and gray matter, but yeah, we just have to live with it. I mean, it's good data set at the end. Oh, this part is really hard. It's probably going like this. Okay, let me back up for a second and let's fill in these big parts. That's why I'm just focusing on the big boundary with a smaller brush than this, because this rest is easy to just fill in with this maximum brush size. I mean, in the really worst case, if we really cannot decide in some subjects this white matter gray matter boundary based on our T2 star weighted data, and once we did this initial segmentation, let's say, and we put a note that, oh, in this such and such subject, I really couldn't see the white matter gray matter boundary for a large chunk of Heschl's gyrus, then we do T1 registration and figuring the boundary out based on the T1 weighted contrast, but not before. Okay, now I kind of start seeing it a bit better. Maybe you notice. See, like that area. This white stripe kind of coming out of it. And that's what I mean. Like maybe the A1 ended, and that's why we are picking up a way better white matter gray matter boundary contrast, as there are fewer axons like entering from the white matter to there compared to A1 region, something like that. Yeah, by the way, you can also download my 2022 paper segmentations. They are all openly accessible if you want to see more examples. I did put my segmentations out there together with the processed images. Smaller brush there. I normally listen to audiobook, but now I need to record myself in silence doing this work. Mm. Save it time to time. Let's see how much we are there. Halfway. Let's do it. Okay, now I will actually try a trick for the rest of it to speed it up. Now I was thinking about it. Just a couple of slices and let's see if it will work. I will do the skip thingy again, every third slice. So 1, 2, 3. 2, 3. I mean, if this works, it will speed up this white matter processing quite a bit. I don't remember if I use this or not now, because it interacts with something I implemented in Laney, and let's see if I was smart enough to account for this. If not, I will come back and just fill in these gaps. Okay, almost there. Okay. Okay. Now, you see in this rest of these slices, I did the 3 jump or the skip trick that jumps across 3 slices. And if what I'm going to use now works, this is very good news for us because it will speed us quite a bit, 3 times. Now I'm going to save it. And then I will actually start using Laney here. Okay, so here I'm going to use first ln2, what was it called? Remify. Input is the segmentation that we did now. Then inner gray matter was labeled 2 because it was green. Outer gray matter, we didn't actually choose it. Let's leave it open for now. And gray matter was labeled 1. Oops. Sorry, outer gray matter was actually nothing. Okay, let's give it 0. Okay. So I'm not sure exactly if this will work or not, but if it works, it will make our lives easy. Okay, so now it reassigns some colors. It's okay. Now, Nemat, after the remify step, we need to get rid of the label 1, this red stuff. Let's call it 6. Oh, sorry. Should be 2. Anything below 2 will be set to 0, but not including 2. Let's see. Yes, this is what I was looking for, just to nullify these ones outside. We just need white matter as label 2 and gray matter as label 3. Maybe we should start from here, actually, at the beginning. I should make a mental note about it. Okay, now let's run ln2 rim polish with actually this one. Dip, 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 dip. Yes, actually it works great. This skipping one step actually works. I think I skipped too many here. Okay, well, we can just fix it by hand. Okay, great. This is good news. Then basically, like, we should start with these 2 and 3s already in the rim format, not 1 and 2 as I was doing with the red. Okay. Well, this is pretty good. As you see, it's getting there. So let me compare it with the previous one just to make sure. Yeah, by the way, this is a good way for you to see the effect of the polishing, where it filled in, where it like separated and so forth. Okay, pretty good. So now I'm planning to basically analyze a disk around here. Yeah, I was saying that probably I need a bit more around here to segment. How can I best get that? Actually, I'm not sure if we need it or not. Okay, let's. Okay, another trick. We can say just clear label and active label blue. adjust the contrast a little bit. And see, now it will only paint on what was clean. Yep, that's the direction. Okay, maybe this is the better view. Yes. Okay. So I'm rushing a little bit because I want to show you the next step that will tell us even more where we are exactly going to be, like super high precision and accuracy. Okay. Now let's switch to paint over blue and active label green to fill in some white matter here. So okay, this is good enough to me. Let's see what does it want. Okay, let's save it as version 7. And let's do the Laney polish again. E007 polish, let's load it. Okay, this is good. Now, the next step And the next step is filling in a little bit of the outer gray matter boundary. So now I'm going to demonstrate it here. Active label 1, and we will go to clear label. Okay. Let's put like this. Okay, now I'm putting a boundary because this is needed for later computing the cortical layers. An outer gray matter boundary that dictates between which boundaries the layers will be computed. And you see that I am leaving this part open on purpose because there is not the outer gray matter. I'm just putting the outer gray matter shell where the CSF boundary should be, like outer gray matter should be. Again, like you don't need to be so precise here. This is not the final precision stage, but a step that leads towards there. And hopefully you are seeing that we are getting there step by step. Maybe once we proceed a bit with this, maybe there will be other ways to speed up the process. I don't know now. I cannot think of it right now. Beep, 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 beep. Oops. Hmm. Okay, I covered it more or less. Let's put on a bit of more work here. Okay, nice. Save it as version 8. Now I'm going to run ln2 rim polish on it again. Hmm. Okay, now let's have a look. Yes, the outer gray matter boundary is a bit better. We don't care about the roughness of this red here. And if you don't want to see it, actually, there's a little trick, which is you can come here to the palette or segmentation label editor and go to label 1 and say hide label in 3D window. See, now it's gone. Now we can see the outer part of the gray matter boundary without that like rough edge that we don't care. Okay, so this is good. Now I'm going to switch to computing layers on this data. Let's call it 9. Okay, ln2 layers. It is just the default values without anything else because everything is optimized for exactly this resolution. So that's why we don't need to worry about anything else. And now, for instance, here, even though we are not at the last stage, I just want to show you the output. I can load the layers as a segmentation output and see. Oop. Now, of course, we hide the red label so it doesn't show it, but yeah, there you go. These are the layers already computed. We are not actually using this one. Now I'm going to go the step beyond, and many people actually don't know this step, but it will be essential for our work, Emily. And I wrote this program, what I'm going to show you next, for exactly what I wanted to do back in the day, and now we are doing together with you for Heschl's Gyrus. Now I'm going to load the mid-gray matter surface. Okay, so this is the mid-gray matter surface. In ITK Snap, by the way, make sure that you go to preferences, and in the 3D rendering, disable the Gaussian smoothing. If there is smoothing, your mesh will look like this with holes. We don't want that. We want the mesh to look without holes and more blocky, which is fine. And that's why we are disabling the Gaussian image smoothing. Okay. So now this is more or less the Heschl's gyrus geometry or superior temporal cortex. And now we might end up segmenting a little bit larger than this, but I think for this video it is good enough. And we can easily extend in the future, not a problem. So now I'm going to kind of locate an area that is more or less at the middle of this Heschl's gyrus. And I'm imagining a disk that would wrap around here. Like a pole there, basically, and take the shape of the local geometry. For instance, this is a good spot. I am clicking here after clicking this 3D toolbar second option so that my cursor moves around where I click on the mesh. Let's say this is a good region. This is a good spot. And now here, I'm going to go there and put a new label, single voxel wide, here. Oops. Oh, just one. Why is it putting two? I never saw it. Wait, what? Why does it put 2? Oh, I never encountered this in ITK Snap. Like, maybe I should downgrade the ITK Snap version because there are a couple of things going wrong actually in this one. Okay, so let's try to make the other one red. I don't know. Okay, fine. Just a single dot. You see single green dot. And now I'm going to save it as control point 0. That's just how I call it. Okay, now we have this control point 0 file. Now I'm going to switch to this other uh, program that I have written, ln2 multilaterate. So this takes a RIM file that we have. This is version 9. Then it takes control points file. We have it here, this one. And it takes a radius input. Radius. Now let's, just for the sake of it, let's put 5, and this is in millimeters. 5 millimeter radius. So it will create a 5 millimeter radius disk around that green voxel that we have put there. Okay, let's run it without any other option. It should be pretty fast because we are in a small region of interest. You see that there are some files coming out like this perimeter chunk, perimeter UV axis coordinates, and now let's explore what these are. Let's have a look at the perimeter first. Let's make a... So okay, now see? So this is a 5 millimeter in radius disk that is grown around the region that we delineated with the single voxel. This is pretty small. Now I'm going to increase it to 10. And this perimeter is the initial guess at the size of the disk, so I can directly load it here while the other stuff is being computed. Okay, see, now it is larger. I think I can go even larger. In my 2022 paper, the size of this disk was 15 millimeter in radius. So if we fit 15 millimeter in radius, we will be basically on the way to replicating what I did for my 2022 paper to analyze the Heschl gyrus. And it might be a good idea to maybe just keep it at 15 and center that the Heschl gyrus because I already have that data processed. So in case if we need, I think 5 more subjects that I have analyzed in 2022 and combine with this data in the future if we want, we will have the same amount of disk already processed. So that's the advantage. Okay, let's load this guy. Okay. So the important thing here is to check for quality control is that this green border should be continuous, which means that without interruptions. Like for instance here, see, we hit a boundary, which means that we need to extend our segmentation a little bit in that direction for this 15 millimeter radius disk to fit. To do that, basically, I am going to load the segmentation here. Yeah, there's a segmentation image. And I'm going to load this perimeter file. I'm not even looking at the other outputs because they will be wrong if this green is not continuous. And I'm going to add another image as my perimeter file so that it can inform me where I should segment more. Okay. And I can make this overlay. Okay, see, I am hitting at the boundary around there, which means that in that direction I need to segment a little bit more. I'm using W to toggle the overlay. Okay, fine, then let's do it since we are here. Yeah, I should have gone a bit further. Again, the same idea. First, put the white matter, gray matter, and then fill in the white matter with green, and then at the end, cover it with the red on top. Now you will see how I would extend the segmentation when we need. Can make this a continuous update. We need a little bit more, not too much, but probably 5-10 slices if we can afford. Okay, one more. Okay, I think this should be good enough. Now I am quickly changing to green over blue to fill in the white matter. Okay. Now I need to cover with the red on top of the clear label. Oops, too much. Okay, fine. Let's keep it as 9. Oh, sorry, 10. Now again, whenever you edit the segmentation, you need to repeat the same steps, which is rim polish. Okay. So let's see. Okay, polished. Let's call it 11. Let's check this. It's smoother as you see. That's what we want. Yep. Okay. Now let's compute the layers on it. We take the mid gray matter file, open it as segmentation. We found the spot where we put our disk on last time. I think it was around this fork that I put it somewhere here. Okay, let's say here we put one voxel as green. Yep. Save as control point 0. Okay, now let's rerun multilaterate. And hopefully our disk will be within the geometry that we segmented. Okay, perimeter came out. Load it here. And yes, it is basically a continuous line, as you see. Our disk is now sitting nicely on top of the Heschl's gyrus. So this area will be parameterized and turned into a disk. Okay, now let's have a look at the other outputs. Perimeter chunk, for instance. Oops, not here. Finish. Something went wrong because it got too elongated. Okay, let's see. And this can happen when you are really at the edge and not exactly there. We can see it from UV axis. These are all important quality control steps, so I'm just showing you like how things are. Normally, I would have segmented a bit larger, but I tried to be more efficient for this video, and of course it broke down. Okay, so see, like our axes are not exactly orthogonal, and this is because probably the perimeter was like just barely inside the region that we segmented, which means that we need to do a better job here. Okay, let's repeat the process. This is just iteration. Like you iterate 2-3 times, it will get there. Okay. Now let's load it as a segmentation as well for me to see. Maybe I missed there was a discontinuity. So this part looks fine. This part looks fine. Yeah, maybe there. Look, there's like one voxel wide gap. We were almost there. Like we almost did it. Okay, fine. Which means that we just need to polish a little bit the segmentation, which was 11. Segmentation, load it. Yeah, I should have done a couple more slides, basically. Okay, let's do it. Save it as a new. I'm going to do 5-6 more just to make sure that next time will work for sure. Okay, this should be good enough. Green, paint over blue. Okay, now let's put the red on top. Oops. Okay, save it. Again, the same steps. Ln to cream polish. Let's call it 13. Ln 2 layers. Mid gray matter output is here. I'm loading it as a segmentation. Okay, here. Now I will put again the, the green guy. I don't know why it does it. Like, this is a new behavior. ITK Snap is getting worse, I have to say, like, and that's why I'm developing my own software, because I think they will, like, for some reason they are getting worse and worse at each version. For what I use, maybe other things are getting better. Okay, control point is labeled. Now I'm going to run multilaterate. Segmentation version 13. And hopefully this time everything will go fine. Okay, let's have a look at the perimeter already. Okay, I think now it is really continuous. All the greens. I'm trying to like optimize the time, but of course, the moment you try to be quick and like avoid some steps, things get harder. Okay, fine. You just need to keep doing it. Open segmentation, load it, finish. And see, that's the region that is kind of giving me a bit of a trouble. I see. It wants to be segmented a bit more. Okay. And we have to do it. Deep, 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 deep. As like I was guessing that this area would be a problem. That's why I was extending earlier in the video. After some hemispheres, you do this, you will get a good feeling of like how much you need to segment. I was segmenting way larger than this at the beginning. But then I noticed that I can just optimize for this 15mm in radius disc. So now a bit going to the insula. Okay, I'll say this is good enough. Green over blue. Fill in the white matter. Okay, now let's switch to red. I'm just focusing on one slide, one axis, as you notice. Because for these slide extensions, it's better to just stay in one. Easier, I would say, not better. Oops, went too much. Okay, hopefully this will be good enough. Let's roll again. Rim polish. Okay, let's call this one 14. And then 2 layers, rim. Okay, mid gray matter file. Let's load it here. Okay, it's a little bit more extended there. Hopefully this time we will hit it nicely. Why does he do this like 2 voxels thingy? Don't get it. Control point 0. Okay, let's switch out up to 13. Oops. Sorry, 14. Okay, now let's see. Come on. Okay, nice continuous line all around. I think it might have worked here. Okay. Let's have a look at the UV axis. Yes. See, now you really feel that they are 90 degrees to each other, geodesically. It worked. Okay. Now let's have a look at the perimeter chunk. Okay. So there are other steps that will come after this that will bring us to the flattening this and looking at the patterns of T2 star, but I want to stop here because we want to have this type of segmentation in all the subjects. So now what we need to do is to load this perimeter chunk as an additional image in ITK Snap. Yep. Okay, let's close the ones that we are not using. Also this one. So now let's load this as a overlay. And now let's go back to our segmentation. 14. Okay. So now comes the really high precision and high accuracy segmentation stage. Because now we know that our really area of interest that we are going to analyze for full precision and accuracy later is this area, this disk that is sitting on top of this Heschl's gyrus. And here we really need to have really good borders for white matter, gray matter boundaries. And that's why I load this file. We can load it like this. And I set it up to be actually having hot color map. I find it easier to understand. And a bit minimum above 1. Okay. So hopefully you can see where it indicates. And now I do my really precise segmentation work. And here we can do like back and forth with you to iterate this further, but okay. See, like now I'm really trying to get the exact boundary as I'm saying, as I'm seeing. As good as possible. I mean, it will never be like exactly perfect, but just making things better. Now I actually don't need to worry about that because my region of interest is only here. Okay, see, like getting these really like precisely the boundary. So this is the way I find it easier to like really ensure that we have good segmentation for Heschl chairs for investigating its laminar patterns. Like this type of high precision stuff is not needed for other analyses, but for this laminar analysis that we are planning to do, absolutely. And there's no way around it. Okay, so basically I can actually stop the video here and send you all these files and the video, you saw that there's a rough segmentation stage that we skip over the slides, then fill in between, then we fill in the white matter, then we fill in the outer gray matter, this red stuff. And at the end, we do this rim polish layers multilaterate iterations to really get the area that we really want the high precision in. And then we do this final high accuracy and precision segmentation work. This is really the polishing part. And of course, like once I am done with this step, I run rim polish one more time because it regularizes the manually edited geometry a bit better to make sure that things are sharp and smooth. Then from there, we will proceed with the other steps of this analysis. Okay, so I'm also tired recording this video. I think I made the point clear. Okay, thanks for watching this long video, Emily. I hope some steps are clear. You really saw me like doing it. I didn't prepare for it beforehand other than computing some of the images. This is really exactly how I proceed with my Heschl Gyrus and Calcarine sulcus analysis. Okay, that's it for today, and see you next time.